Lagrange Interpolation. Lagrange interpolation is represented as f of n of x equal to the summation of Li of x times f of xi, where I is from 0 to n. Also, L of I of x is equal to the continuous product of x minus xj all over xi minus xj, where j is from 0 to n and j is not equal to I. Now, to make the MATLAB code for this one, it can be seen that we have a for loop here. And this one, to assess for the continuous product, we have to use for loop. First, we will input the variables with x equal to 1 for negative 3 and 3 and f of x is equal to negative 4, 59, negative 32 and 22. So we'll use input x and y equal to input y. Now, for us to assess how the for loop is made, let's expand this term. So for I equal to 1 and j equal to 1, because for I equal to 1, we'll evaluate Li of x, then we go here. So we will assess j equal to 1. In MATLAB, the counting starts from 1, so we'll not use 0. We'll start with 1. So we have x minus xj all over xi minus xj. But take note that j is equal to I, so we will end the iteration here. So we have I equal to 1 and j equal to 2. We have x. For this one, we have x minus x2 all over x1 minus x2. For I equal to 1 and j equal to 3, we have x minus x3 all over xi minus x3. And for I equal to 1 and j equal to 4, we have x minus x4 over xi minus x4. This would be for Li of x only, but we have to multiply all the functions here. So for this one, we'll skip this one and we go to the next iteration. After that, we will multiply this function to this next iteration. For us to multiply this one, we have to save it to a variable a. So we have to multiply a to x minus x3 over xi minus x3. To do that, we have a times, that would be x minus xj over xi minus xj for the multiplication. In MATLAB, that would be conv. We'll use the function conv. When we say conv a p, that is equal to a times p. So for this one, this would be conv a with x minus xj all over xi minus xj could also be simplified further because xj is written as poly xj is equal to x minus xj. So we'll replace x minus xj with poly xj. That would be a is equal to conv, that is multiplying a with poly xj all over xi minus xj. This would be our iterative function for the equivalent of the Lagrange term Li of x. So writing it in a for loop, we have to use for I equal to 1 to n for this one. Then we'll go to the next loop, which is another for loop for j equal to 1 to n. Take note that we'll need the value of n. N is the number of sample data, so that would be n equal to, list the function length. We'll count the number of x or y. For me, I will use y from 1 to n. Then take note that we have also another one. If j is not equal to I, then we evaluate this function. So we put another if function, j is not equal to I, then we evaluate this iterative function a equal to the product of a and poly xj all over xi minus xj. Then put end function for the if closing, and we put another closing for this one. But for I equal to 1 to n, to take note that we have to multiply it to f of xi, and that is the value of I. So next one, we will multiply the end value of the iterative product of this one. So from 1 to n, we get the product, and then we multiply it to yi. That would be yi, and then we will save this first iteration into a matrix, because it is easier to save functions, because this one is a function. It is in terms of f of x. In MATLAB, it will be simpler if we will save this into a matrix first. Before we can save the matrix into the matrix, we have to define first what the matrix is. So I want the matrix to be L, but we have to determine first the dimensions. When you say matrix, that would be n by m. This is the row and this is the column. So how many rows and how many columns are there? So for this one, we have a 4 data sets. We have n equal to 4. If you access this one, this is a constant and this one is a constant. So Li of x will be the determining function if how many variables are there. So for this one, we have this is 0, and this is a first degree times a first degree times a first degree. We have a third degree function. When we say it's a third degree function, that would be x cubed plus blank x squared plus blank x plus blank. So for the first iteration, the function would look like this. For this one, we have 4 data sets, and then we have 4 iterations. So we will have 4 functions of this one. We have x cubed plus x squared plus blank x plus blank. Then we have x cubed plus blank x squared plus blank x plus blank. So we have how many rows? 4, and we have 4. So we can conclude here that we have a 4 by 4 matrix, which is a square matrix. So as you can see, this one is the value of Rn. So we can conclude that for matrix L, that would be n by n matrix. Then I want the matrix to be equal to zeros first. So what does it mean? So for the matrix, what is zeros? N by n. This would mean 2, 3, 4. We have a 4 by 4 matrix with 0 values. And then we'll save this first function in the first column. So to save that, we will have a colon comma, and since this is for the first iteration or the ith iteration, we'll use I. Then we put end function. Now for the second iteration, it will evaluate again for L2 of x. For this one, then we'll multiply to y of 2. Then it will save for the Li, which is the 2. Second row, it will save it in the second row. Third row, save it to the third row. For the fourth iteration, it will save in the fourth row. Now, finally, we have to get the sum, because it indicates a summation here from 1 to n. That would be P is equal to the sum of matrix L. So we'll get the sum of all these functions to get the equivalent function that fits the data points. Now, we can display the function using the function this, or the code this, approximate polynomial this one, the equivalent value would be blank x cubed plus blank x squared plus blank x plus blank. So this one would be p of 1, this is p of 2, p of 3, and p of 4. Now I want to display the values of this one together with the text x and cubed. Then we have x squared, then x. I'll use for loop for that. For k equal to 1 to n, use f, print f. I want it to display on a new line, and put plus first, and then a 4 decimal place, p of k, because I want to display first the p of 1. For the first iteration, that would be 1, so p of 1 would be the first coefficient of the highest exponent, and we put the variable x raised to the value of the exponent would be for k equal to 1, that would be n minus k. N minus k would be, for this particular example, that would be 4 minus 1, 3. So the exponent would be x cubed first, which is p of 1. Now we put n here. For example, we want to get the value of, or approximate the value of y at some particular point to approximate. Then we can also do that. Let's just introduce another variable, point to approximate is equal to input. We have to ask first the user what is the particular point to approximate. Then if the user inputs the point of to approximate, say 12, it will store to this variable, and then we can solve for py as the value, the value of y for that particular point to approximate, using the code polyval p, then variable point to approximate. Now we can also display this value, so in this f, print f. Then I want it in a new line, so the value of, or at x equal to, say, 4 decimal places is of 0.2 approximate is %t, and that is p of y. Now if we try to solve this function, the answer is equal to x cubed minus 5. Let's try to put this code into MATLAB so that we'll know if we can get the value x cubed minus 5 as the answer. Let's review first. We have I equal to here, as you can see, we have on the first iteration, we have to put the initial value of a, because if we have on the very first iteration, it will multiply this polynomial to a, which is an unknown variable. So we have to introduce first what a is. That is equal to 1 as initial value. We cannot use 0 because it will multiply 0 to a polynomial, then the value of the iteration will be all equal to 0. I think this is good. Now let's see in MATLAB how the code works.